So hello everyone, welcome to our RKHS seminar series. And today's we're going to have a talk from Arbel, who's a research scientist at INRIA. Actually, he also worked in the same team with Julian Mariel, who is another professor that I wish to invite for this seminar series anyway. And also, Mikhail is a student of Arthur Gretton, and Mikhail Arbel has graduated from École Polytechnique with a master's degree and with the PhD advisor of Arthur Gretton at Gatsby Computational Neuroscience Unit of University College London as a PhD. And actually, his research interests include unsupervised representation learning, non-convex optimization, and also machine learning with high dimensional sampling as well. And mostly he applies these theories and the research areas into some real world applications in natural sciences and physics. So welcome to our seminar series, and we are very glad that you accept our invitation to present today on functional bilevel optimization theory together with algorithms. Thank you for coming.
Well, first, thank you, Omar, for the nice introduction and for the invitation. It's a pleasure to be here today. And yeah, so I've been working on bilevel optimization in general since I joined INRIA. And I've been trying to look at for applications in natural sciences, but not only in machine learning in general as well, but also to extend these methods because as you'll see, they can tend to arise in different contexts, and but they are typically hard to solve. And so what I've been doing is trying to find ways to make them work. Okay, so let me start just with an outline. The first two parts of the talk will not be about kernel methods, but the last one will talk about kernels. So that's my promise. So I'll start by just giving a motivation for bilevel optimization in the context of machine learning and highlight some of its objectives and challenges. And this will lead us to one line of work that allow us to overcome some of the challenges, which is the first part of the contributions, I would say, that we call functional bilevel optimization. And then the last part will be about applying this framework in the case of reproducing kernel Hilbert spaces in order to get some theoretical insight, more precisely on learning theory. Okay, so let's get started by the motivation. And please feel free to interrupt me with questions. That would be, I'm very happy to clarify things. There will be some equations here, so I'll try to keep it high level, but it's essentially a technical topic, so it's hard to avoid equations. Okay, so let's start by explaining what a bilevel optimization is. This is basically a problem that has a nested optimization structure. What I mean by that is that you would have two objectives, not just one, and these objectives are interdependent, meaning that you will have an inner, what we call an inner level objective, which needs to optimize a parameter or a variable theta, while another variable omega is kept fixed. And once you find the optimal solution, this optimal solution theta depends implicitly on the other variable omega that we call here. And then you feed this solution to the upper level, which tries to optimize with respect to omega. Okay. And here the big difficulty is that there is a dependence on omega that is implicit through the solution of the inner problem. Okay. And the goal is to optimize this or solve this problem, meaning that we try to optimize the upper objective and the lower one using gradient methods, okay? And we'll see that this poses some challenges. And let me just start with a motivational example. This is something that essentially occurs every time in machine learning. So in machine learning, you have some data, let's say the blue dots here, and you'd like to fit a model, for instance, by solving a regression problem, and the model is supposed to fit the data, okay? So the model would have its own parameters, and you are trying to find the optimal ones given your data set. The problem is that in general, you need some sort of regularization to avoid overfitting. Okay, for instance, on the left here, if you don't really regularize well your model, you'll get a poor fit. You'll get an overfitting here. And then the amount of regularization, you can parameterize it by some additional variable, which would be here omega, and that would be the hyperparameter that tells you how much you need to regularize your model. The problem is that you don't really know how to pick that hyperparameter. So a typical way to choose it is by doing cross-validation. And what I mean by cross-validation is that you pick several values of the hyperparameter. For each one of them, you can fit the model using that particular value. You fit that model on the training set. So you have some data that is specifically used for training the model. And then you leave some additional data called the validation set. And on this set, you will evaluate the performance of the model. And you do that for all these different choices for hyperparameter. And then you pick the one, the hyperparameter that performs the best. So that's one way to select the best hyperparameter. And it's done by exhaustive search. You really choose a grid and try to look at all possible alternatives, choices. And this is effectively what is going on is really solving a bilevel optimization problem where the outer level is the validation objective and the inner level is the training objective. The problem is that's okay if you have just a single hyperparameter. If it's just a scalar, you can do that. But if you have much more hyperparameters and it becomes like a huge vector, then you cannot really do grid search. And maybe a more efficient method would be to use gradient methods. So you try to do gradient descent on the hyperparameter, okay? And the whole goal of this topic of bilevel optimization is to find efficient ways for approximating the gradient of the total objective here. Okay, so this general formulation has many applications in machine learning. And the first one, which I mentioned previously, is hyperparameter optimization, so selecting hyperparameters. But there are also a lot of other problems. It has been popular for meta-learning. That's a sort of problem where you try to learn a single model that will be easily adaptable or adapted to several tasks. There is also another application on reinforcement learning, and in particular, model-based reinforcement learning. We'll see a little bit more what we mean by that, and I'll show you some applications or examples. Generative adversarial networks, probably if you heard of them, these been very popular for generating very realistic, complex distributions like images. And the way they are trained really looks like a bilevel optimization problem. And there are some recent work that really try to exploit these methods for learning or training GANs. And then there have been some older works by Julien Méral, where he used the framework of bilevel optimization for learning sparse dictionaries for representing data. Okay, so this was really about introducing the problem. The bad news is that general bilevel optimization problems are very hard. And some recent work has shown that it's even harder than NP-hard problems. It's a level above them, okay? I won't go into the details of that, but if you are interested, you can check out this recent work by Bolt and co-authors. Of course, the question is, can we still do something in specific cases? And the answer is yes. There are some particular cases where you can solve bilevel problems easily. When I say easily, it means at least computationally, it's not NP-hard. And the main setting that was considered in the literature is when the lower level problem is strongly convex. And strong convexity here it's a classical notion in optimization. It ensures that you'll have a unique solution. And this is very important. And the second point is to have a finite dimensional variables. Okay, all the variables are finite dimensional. So if you have these two ingredients, then you can hope to solve the bilevel problem efficiently. And what this says is that we cannot hope to just consider very generic bilevel problems. We need to restrict to some particular function classes. Okay, so let's talk a bit more about this nice setting that was considered, which is the strongly convex lower level with finite dimensional lower variables. And there is a general recipe that can be used to solve these sorts of problems. So keep in mind here, we are interested in using gradient methods. And what this means is that we want to at least be able to compute the gradient of this upper or total objective. I'm going to call L the total objective. So if you are able to compute that, then you can perform gradient descent on the parameter omega. And that's exactly what you want. So here, just by applying the chain rule, you can get an expression. What's important in this expression is that, well, it contains some partial derivatives of the upper objective evaluated at the optimal solution, theta, which comes from the lower level. But not only, it also involves the sensitivity of this optimal solution with respect to omega. So these are two things that we need to be able to compute in order to evaluate the gradient. So theta star is fine. Since you are strongly convex, we know how to optimize the inner objective and you can find a good approximation to the solution. But for the Jacobian or the sensitivity, what you can do is to employ the implicit function theorem, which tells you exactly what's the expression of the Jacobian. And the expression of the Jacobian is just obtained by solving a linear system. And this linear system involves the second order derivatives of the inner objective. Okay, so on the left is the Hessian with respect to theta, and on the right is the cross derivative. So between like differentiating with respect to the first argument, then the second. Okay, so this is a linear system that is in finite dimensions. You can solve. You can even approximately solve it in efficient ways. And indeed, there are a lot of algorithms that are scalable and efficient that works well in this particular setting. They have been studied, so we have guarantees about their convergence, which are nearly optimal in various settings. So deterministic, when you have like a finite set of data points, when you have infinitely many of them, which you can call the stochastic setting, where you see data points at every iteration, you see new ones. All of this was analyzed. So it's a manageable setting where we can solve the problem in a convenient way. However, it's a very restrictive setting in machine learning. Why is that the case? Well, simply because often the parameter theta of the inner variable is just something that parameterizes a predictive model. Okay, and for instance, typically the inner objective would look like some regression loss plus a rigorization. This is like the easiest example I could come up with, but there are much more interesting examples. So this is just to give you an idea of what's going on. And so theta essentially parameterizes a model. And if you require strong convexity with respect to theta, then this is essentially restricting the model to be linear. just have a linear model. Okay, that's nice because linear models, they are interpretable, and we have this strong convexity, so we can apply all the algorithms that are existing. However, this is restrictive in terms of expressivity of the model. If you would like to capture some nonlinear dependence in your data, then you might want to use something a bit more flexible, such as a neural network. But as soon as you use a neural network, then the objective becomes non-convex. And then you lose all the nice framework or guarantees that we had before. So should we go non-convex? Well, as I said, the advantage is that you can have access to more sophisticated models, but then there are two bad news. The first one is that you can no longer apply the implicit function theorem, which tells you how the solution depends on omega, okay? And a reason for that essentially is that you don't have a unique solution, you might have multiple ones. And that's even worse news because having multiple solutions means that the whole bilevel problem is not well defined at all. It just doesn't make sense because depending on the way you pick the solution, you end up with a different objective for the function L.
What about when you now take quadratic functions, convex functions instead of linear functions?
Right. So you could use quadratic functions, and this can be, in the end, just expressed as a linear model. If you choose your feature here, this is an arbitrary feature. If you include second order moments, then this will actually model quadratic functions.
Okay.
Right. Yes. But still, it has this flavor of being having a linear dependence on the parameter. And that's what can be very limiting. Yeah. Especially if the parameter is finite dimensional. Now, if you allow the parameter to be infinite dimension, that's another story, and we'll go back to it. But for now, yeah, it will be limited. Okay, so there is ambiguity as soon as you have non-convexity, and this particularly occurs when you use neural networks that are over-parameterized, meaning that they have so many parameters that they can fit your data exactly and fit it in many, many different ways, meaning that there are several parameters that can allow you to fit your data exactly. And that's really a big issue. So to address that, in the first work, what we try to do is to try to make sense of all this setting, of what happens in the non-convex bilevel setting. And for that, we introduced a notion of a selection map, which will be used as a replacement of the solution. And I remember the solution of the inner problem is ambiguous because there could be many of them, and you need a way to choose a particular solution. And the selection map is a way to choose it. And what is nice about this notion of selection map, you can just define it mathematically, but you don't need to compute it explicitly. You can obtain it implicitly using an algorithmic procedure. For instance, just by picking an algorithm that optimizes the inner objective, starting from some initial condition θ0, in the limit, that will give you a stationary point, and this point here would be the selection map. Okay, if you consider all possible stationary points that you reach depending on initial condition. So using this notion of selection map, we show that you can still obtain a formula for the gradient that is essentially the same as the one you get when you apply implicit differentiation. So here, the important point is that you cannot really apply the implicit function theorem. You have to apply something else to recover a similar expression. And we show that this holds for some class of suitable functions that we called parametric Morse-spot functions. So Morse-spot is functions are something that is classical and studied in differential geometry. And we extend that notion to include a parameter, which is this variable omega. Okay, so the whole point of this study was to justify using standard algorithms even when the inner loss is non-convex. This can still make sense. However, this doesn't really solve the problem because you can still get instabilities in practice because you would have to still solve this linear system, which might be ill-conditioned, even not invertible. You might have issues. And even if you'd like to analyze convergence for this sort of algorithms, that would be beyond reach because of the non-convexity of the objective. We don't really know how to provide convergence guarantees in generic non-convex for generic non-convex problems. Are there questions about this part so far? Okay.
From my side, no, but I think you are going to put all of these into reproducing kernel space.
Yes,
and then
I will.
The convergence and the selection map will appear immediately.
Exactly. Yes.
Okay. Thank you.
That would be the idea of the last part. So we'll get there, and exactly that's the thing. So we've explored a first approach where we try to get rid of strong convexity and just have non-convex things, but we've seen that it's maybe not such a good idea. So maybe let's keep strong convexity, but maybe you can increase expressiveness of the problem by allowing infinite dimensional variables instead of finite dimensional ones. Okay, and so this is the approach that we're gonna dive into very soon. So going infinite dimensional increases expressivity, okay, can go beyond linear models, and also open ways for theoretical analysis. So that's exactly what you guessed. Okay, so the first part is to introduce this generic framework, which we called functional bilevel optimization. And we'll see that although we are dealing with infinite dimensional spaces, we'll still have practical algorithms. So this first part will not be so much about kernel methods. We'll still be using deep networks. And then the second one would be about kernel methods. Okay, so this is joint work with our PhD student, Sieva, that is jointly supervised with Julien. So let's take a look back at the example that we looked at. Okay, so we have this bilevel problem, and typically in machine learning, the objectives would have the following form. Okay, not exactly this form, but what is important is that the parameter or the variable theta is here to parameterize some predictive model, and all what we care about are the predictions of the model. So both objective in the inner and outer only depend on the function evaluation of this model. So the parameters do not matter that much. They just allow you to represent the function, but what you care about is the function evaluation. And you could choose a different parameterization of the family, and this wouldn't change the predictions. So since the parameter or the variable theta does not appear explicitly or independently from the model, why not just using the model directly or the functions as the inner variable instead of the parameter theta? And if you do that, then you get something that is much nicer. So here what you just do, you just replace all these parameter theta, just replace it by a function, h of x, and this would be the prediction function that you are looking for. And this will be the inner variable, and it will be allowed to live in a Hilbert space. Okay, for now, I'm not saying anything about the Hilbert space. It's just some abstract space. And if this space is very rich, then you have a lot of flexibility in terms of finding a good solution. The other thing that you gain is that strong convexity becomes something that is easier to achieve in abstract functional space. And this is one particular example, because Since H is in a Hilbert space, both objectives, or at least the second one, more importantly, is strongly convex in H. And these objectives are the ones that you encounter very often in machine learning. So that's good news. The fact that we are optimizing over a big Hilbert space doesn't mean that we have to do the search in this big space. We can still, in practice, restrict to a parametric family when we are optimizing concretely. So you can still use function approximation. It's just that the problem that you are trying to solve does not depend on the way you are parameterizing or approximating it. Okay. And what we will be doing now is to perform implicit differentiation directly on the inner solution, which is a function now and not just a vector. So this implicit differentiation will be completely independent of the way we approximate that very solution. So it will not depend on the parameter that is used for approximating it. And that's really the key point that allows to get robust and more stable algorithms for bilevel optimization. Okay, so I'll start with just a result that we provide, which looks really like the implicit function theorem, which is something very classical, but there is a slight twist to it, and it makes it actually slightly general. And that will be exactly what we need for our setting. So here, what we're going to do, we assume that the inner objective is strongly convex in its second variable. And we said that this condition is not so hard to get in practice. That both objectives are finite, okay, well-defined, and Fréchet differentiable. So Fréchet differentiable in both variables, omega and h. And here, the notion of Fréchet differentiability is a strong notion of differentiability. But this is fine. You can make sure that you can come up with losses that satisfy that. And now you need an additional condition to apply the implicit function theorem, which is that the the partial derivative of this objective in its second argument is differentiable, but in a weaker sense. And this sense here is called Hadamard differentiability. So in finite dimensional spaces, both Hadamard and Fréchet differentiability are exactly the same notion, but they are very different in infinite dimensions. And we need just the weaker notion. So when you have these three assumptions, then you can show that the objective, the total objective, is differentiable, and you still have the same sort of expression for its gradient, which would involve a Jacobian. And this Jacobian is itself a solution to some abstract linear system. Okay? When I say abstract linear system, it means that you need to, it involves some operator in your Hilbert space. And this acts as a matrix, essentially, a matrix that is infinite dimensional, that you need to invert. Any questions for this? Okay, so why do we care about Hadamard differentiability? Of course, there exist standard versions of implicit function theorem, but these would require the partial derivative to be Fréchet differentiable. What we find in our setting that we'll see in the next slide, that this condition is just too restrictive. In practice, there are many spaces. If H is an L2 space, then there's been some old results by Nemirovsky and Semenov that show essentially this condition only holds for quadratic functions. Okay, it means that the objective L in, must be a quadratic function of H, which is already a good thing. Regression problem with the mean squared error is a quadratic in H. But if you want to use other objectives like cross entropy or some other things that are not quadratic, then you don't have the Fréchet differentiability. On the other hand, having Hadamard differentiability allows you to extend much to a much broader class of functions that includes many of the functions objectives that we consider in practice. And this notion, by the way, is also used in statistics for the functional delta method. So it doesn't come from nowhere. But I believe this was the first time that it was considered in the context of optimization and to provide a differentiability result. And we haven't seen it elsewhere. Okay, so for now, we have just an expression that is independent of the way that we are approximating H. So it means that if you approximate H with a neural network, even if things are non-convex, that's fine, because the expression that you get, the abstract one, is still well defined and is totally independent of the parameters of the network. The problem is that this expression is abstract and we don't really know how to use it in practice. So what we need to do is to consider more concrete spaces. And this is what we do. We consider L2 spaces, so spaces of functions that are square integrable with respect to some data distribution. Here, I call it P. And moreover, we consider some specific structure in the losses. So both objectives, outer and inner, they are expressed as expectation over this data distribution of some pointwise objectives. And this is a setting that you find everywhere in machine learning. So it's not really, it makes it relevant here. So for instance, in regression, we really have that. And we are looking for a prediction function that is square integrable. So we are really searching in the space of L2 functions. And so for this particular setting, we have a more useful result, which provides, I would say, a more explicit expression for the gradient. So here the gradient is expressed as an expectation of partial derivatives of the pointwise losses evaluated at the optimal solutions, okay, H star. But it also involves some other function that we call the adjoint function. So if you're familiar with the I think in dynamical system and control theory, this is an object that appears very often. So what is this adjoint function? It is also an element in L2 that minimizes what we call the adjoint objective. And this adjoint objective is here in our case, it will be a strongly convex function in A that involves some second order derivative of the pointwise loss. What is important here to note is that all these derivatives are only with respect to the output of of H. Okay, so we don't need to differentiate further than that. Don't know if this is clear, but maybe I guess what I'm saying is that this is just the derivative in terms of the second argument of L. What is nice about this expression is that now we can approximate A and H by some parametric family. And if you have data or samples from P, sorry, there is a typo here, Q should be P, then you can just, approximate these by empirical averages. And that gives the general recipe for an algorithm that we proposed that we called functional bilevel optimization. So we approximate the search space for both the prediction function and the adjoint function by some flexible parametric families, for instance, a neural network. And then you can optimize these families using any optimization algorithm, and typically stochastic gradient descent. And once you optimize it, you can obtain an approximation of the inner solution. Once you have that approximation, you can now approximate the adjoint function, again, using stochastic gradient descent on the adjoint objective. And once you have this approximation, you can just plug them into an empirical average to get an estimate of the total gradient. So this is the approach. And although here, to optimize the parameters of the networks, we are solving a non-convex problem, this does not affect the original problem, which is still well defined and still makes sense. And that's really the key contribution, in fact, is that you can still solve non-convex problems that we know how to solve using, like in deep learning. We are okay with the solution that we get, and you can just plug them into an estimator for the gradients. So there are some advantages of this, which is in terms of computations, you have memory and time savings. So no need for higher order derivatives of these models in terms of their parameters. This does not appear anywhere. And these algorithms would typically be more stable, and compared to the approach that only uses the parametric bilevel optimization. Okay, so let me show you quickly a few applications. The first one is instrumental variable regression. And if you attended Arthur's talk, probably he mentioned that. So this is a classical problem in maybe causal inference. I won't dig into the details. You can look. You can read some papers. You can also look at what we say in the functional bilevel paper. But the take-home message is that IV solves a nested regression, which typically can be expressed as a functional bilevel problem. And you can choose the regressor functions to be deep networks. And that's what was done first a few years ago in this paper, with which we compare. And what we do is that we just essentially compare different algorithms on some synthetic task provided in that same work. And what we notice is that there is really a huge improvement over classical bilevel optimizations. Here is approximate implicit differentiation, and this is called ITD, so iterative differentiation, where basically you're just not taking at all the functional structure into account and just performing implicit differentiation in the parameters of the neural network, which is something that we've seen is maybe not such a good idea. So here the lower is better, and what we get is the least out of sample error. Okay, it's also competitive with a method that is specifically designed for instrumental variable regression. Then maybe a second application is for model-based RL, which has been shown in this work that it can be expressed also as a bilevel problem. But what we show is that it also has a functional bilevel structure. And when you take it into account, then you get a method that works well in various settings, while that was not the case for previous methods. You could have method that would work well in a particular setting, which here on the left I'm calling misspecified setting, where you are using a model that is not expressive enough. And then if you use a model that is suddenly more expressive, you will have another method that works well and not the previous one. So what we show is that using functional implicit differentiation, you get something that works well on both cases. Okay, so let's talk a bit about theory. So we try to provide a convergence result for this algorithm, and but this is hard, and we'll see why this is hard. So what we consider here is just a simple update rule where you have your estimator of the gradients, and you can use it in an approximate gradient descent scheme. So this is the update rule of the iterates. And what we show is that on average, the squared gradient for the true objective will shrink to 0 if you look at the smallest value of it. So this is a typical quantity that is controlled in non-convex optimization. And what we show is that this quantity will decrease with 1/t. T is the number of iterations that you perform, but then there will be some additional terms. This first term is just due to the variance because there is noise in data. This we cannot do much about it. But then there is 2 other terms, and these terms are the errors of approximation that you are making because you are using neural networks instead of optimizing over the whole L2 space. And so you'll have an error for the inner solution and an error for the adjoint function. The problem is that we don't really know how to control these errors when we are using neural networks, because this depends on the optimization quality, whether it reaches a global solution. For a non-convex problem, it's hard to guarantee. The approximation power of the family that you are considering, whether it's rich enough to well approximate the true solutions, and also the complexity class of the neural network family, whether it tends to overfit or not to the training data. And as a consequence of this challenge, the rate that we get does not quantify the effect of sample size. So here we don't know whether the error decreases if we increase the number of training points, which of course we expect it to decrease, but it's not apparent here. So can we get quantitative convergence results? Well, maybe it's hard in L2 spaces, but what about other spaces? And that leads me to the third part of the talk, which is a learning theory for kernel bilevel optimization. And that's where we really consider RKHS. So this is a joint work with Fares, which is another PhD student that we co-supervise with Edouard Powell and Samuel Veiter. So Edouard is in Toulouse and Samuel is in Nice, both researcher that works on optimization and also bilevel optimization. Okay, so let me introduce the setting here. It's similar as before. The only difference is that H now is an RKHS with some kernel K. The objectives are both also expectations over some data of pointwise losses, but here we need to introduce some rigorization in terms of the RKHS norm of H. And the reason for this is to ensure that the inner objective is strongly convex. Okay, and this will be key in this study. So we are not the first to come up with this formulation. This have appeared a while ago, but the object of this study is to provide a generalization result for these problems. So why do we consider RKHS? Well, you have more expressiveness because some RKHS can be dense in L2 spaces. So we are still in infinite dimensional spaces of functions. We can approximate almost anything. The algorithms are easy to derive thanks to representer theorem, which we'll see in the next slide. And also, the RKHS setting is a well-established theoretical framework that was available for regression problems and similar problems, not for bilevel problems, and that's what we will do here. So there is some ground for learning theory. Okay, so first, from an algorithmic perspective, when you have access to n samples, you can turn the bilevel problem into a finite dimensional one using the representer theorem, which is probably something that you are now familiar with if you have been studying the RKHS setting. So here, the idea is that you get n samples. To simplify, let's say, take IID samples, and then replace all the expectations by empirical average. And then the representer theorem ensures that the solution, the optimal solution for the inner level, can be written as a linear combination of kernel evaluation at your training point with some coefficients. And these coefficients are obtained by optimizing this empirical version of the objective. And so in the end, your bilevel problem becomes something that is finite dimensional, where the inner variable is a vector of dimension n. So we have as many components as the training points. What is nice about this is that you can apply existing algorithms for bilevel optimization. So the ones that were designed for strongly convex setting, you can use them, they would work, you can have guarantees for that, that's fine. And more precisely, if you are interested in computing the gradient, then this involves expressing the Jacobian of the parameter with respect to omega, and this has an expression, so you just need to solve a linear system. The problem is the dimension of theta increases with sample size. Of course, this has scalability issues, but not only. We'll see that this poses a challenge if you want to do a statistical or learning theory.
Okay, sorry.
Yes.
These are derivatives, right? The derivatives matrices.
So yes, so these are partial derivatives.
Okay.
Yes.
I couldn't see that.
Yeah, I remained vague here because in the end, it's not too important. What is important is to notice that this vector here is something of size d times n, and n is the sample size. So if you increase n, then this increases. But yeah, these are quantities, the partial derivatives, you can evaluate them on each data point and you collect them into a matrix. So that's what the D here is, yes. Okay, so let's see what are the challenges for having a learning theory for this problem, the kernel bilevel optimization. For that, we can look at the existing generalization results for bilevel optimization. And one thing that one should note is that all these results, they require the inner level parameters to be of fixed dimension. Fixed means independent of sample size. And the intuition behind that is that if the parameter here was fixed dimension, then this parameter and its gradient, you can expect it to approach some population counterpart as n increases. So when n is infinity, then you just recover the solution of some original bilevel problem, abstract one. And then you can even quantify the rate, which typically would be 1 over square root of n. And once you have that, you can provide generalization results, which are based on controlling how much the estimate or gradient estimate is far away from the true gradient when you have access to infinitely many points. So L here is the setting where you just have expectations of your data, and L hat is when you have just n samples. And so this can be controlled in terms of how far the estimator theta hat of the inner solution is from the population counterpart, and the same for the Jacobians. Okay, so the problem with KBO is that the dimension of the parameter theta grows with n. And this means that there is no notion of limiting vector as n increases. So the parameter theta doesn't converge to anything. And that's a problem because the expression of the estimator of the gradient depends explicitly on these vectors, theta and its Jacobian, which grow with n. So we cannot really use the existing convergence results because they are really for fixed dimensions. But then maybe what we could do is try to get an alternative expression of this gradient estimate that is independent of the parameter theta and the Jacobian. And this is what we do in this work. So let's rethink a little bit the expression that we got for the gradients. We obtained it in 2 steps. The first step is to replace the true objective by some estimation of it using finite samples. And then once you have it, we applied implicit differentiation. So this corresponds to first discretizing the problem, then applying the implicit differentiation. The advantage is that it's convenient in practice. You can use the estimator that you get, you can compute it, but then we've seen that it's hard to use for statistical theory. But what if we followed a different path to obtain maybe an alternative estimator? What we could do is to first apply implicit differentiation in the population setting where we have infinitely many data. And once we have an expression of the gradient, we can discretize it, okay? So when we apply implicit differentiation in the RKHS, you can get an expression for the gradient. And this expression will involve two functions, the inner solution H star and the adjoint function. So this is really similar to what we've seen before. Just here it's for the RKHS. And once you get the expectation, the expression, you can discretize it because it will have a form of some expectation. And you can replace these optimal solutions by some empirical estimates. The expression that you would get is not very practical because it involves some functions that you need to approximate, but it's easier to control the error between the gradient, population gradient, and its estimation in terms of these two errors, of how much the inner solution is well approximated by its empirical counterpart, and the same for the adjoint. What this means is that we could use tools from learning theory to control these errors. And one result that we show is that both paths, they lead to exactly the same estimators. You do these two different approaches and you obtain exactly the same object. And this is nice. So now we can say something, some theory results about a practical estimator that we can use. And let me tell you first the first result, which is a maximal inequality that allows you to control the gradients, the error between the true gradient and its approximation uniformly over the parameter omega over some compact subspace, any compact subspace, and this in expectation over your data. And what we show is that this decreases as 1 over square root of n, which is nice. It's kind of the parametric rate. And I doubt you can do better unless you have much stronger assumptions. I'm not talking about the assumptions here. They are mainly regularity assumptions like smoothness. We assume that the kernel is bounded, but these allow for a relatively large setting. And now, how do we use this result? Well, we can use it to obtain some convergence results for bilevel optimization. So here we have a corollary where we have some iterates that are computed using the gradient estimator. And if you further assume that the outer objective, the pointwise loss, is coercive in its second argument, meaning that basically it grows as a quadratic as you go to infinity, then you can control the gradient of the loss along the iterates on average. And this will decrease or will have two components. One optimization component, which is 1 square root of t plus 1. And this decreases as you increase the number of iterations. But then there is one incompressible error, which tells you, okay, if you have just n data points, then you'll still suffer an error of 1 square root of n. So you need to increase the number of data points to make it smaller. Okay.
But it is interesting that now the error getting smaller with the increasing number of iterates.
Yes. So as you increase the number of iterates, you are converging towards a stationary point for which the gradient will be 0. But then it won't be exactly 0 because you have only finite number.
Yes, but a kind of fixed point here.
Exactly.
Something like this. Oh.
Exactly. Yes. And this was not possible to obtain in the previous analysis because
yes, it's clear.
Yeah. So maybe I can say a few words about how do we get this result and some small challenges that we had to get this maximal inequality. That won't take long. So the main strategy is to first find an upper bound on this error that is pointwise in terms of errors that are of this form. So you're comparing some empirical average with its population counterpart. And this is for a family of functions. There are several of them. And some of them would be real valued functions, but some of them will be RKHS valued. So there would be elements in an RKHS, and they are evaluated at some samples. And now for the real valued functions, you can apply some classical results in empirical process theory, which are basically maximal inequalities that exactly tell you this quantity here should decrease as 1 square root of n. But for RKHS values functions, you cannot really do that because empirical process works when you have real valued functions. Instead, what we show is that you can use another type of maximal inequalities, but for U processes. And U processes is a generalization of empirical processes where you are dealing with U statistics. If you're familiar with the notion, if not, that's fine. You can check that out in the paper. And the way we apply that is just by computing the error, the square of this norm here, which involves make appear a U statistic, which is a real valued process, but that is a bit more complicated than an empirical process. And there you can apply the results and you get the rate that you want. We applied some other approaches, but these all led to degraded rates. So really using this notion of U processes were very key to obtain the parametric rate of 1 square root of n. Okay, so that was for the proof sketch. This leads me to the conclusion of this work. So what we did is that we introduced a new framework for bilevel optimization. What is nice, I think, about it is that it is compatible with flexible function approximation tools. It leads to practical algorithms that seem to be more stable, and there is reasons for it to be stable, theoretical ones. And it also opens the way for having a learning theory for these methods. Of course, there are limitations. Here we consider two functional spaces, L2 spaces and RKHS. I think what could be nice is to extend to even further spaces, such as Sobolev spaces. And why this could be interesting, because it will leads to a path for learning PDEs. So if you have a partial differential equation that is parameterized by some unknown variables, then you can use this framework, the bilevel framework, to learn these parameters. Also, what would be nice is to have a generalization theory that is beyond RKHS. Maybe that covers deep networks. We have some ideas for that because there's been a lot of work on generalization for deep networks, exploiting what is called the neural tangent kernel. So that could be one direction to explore. And yeah, that's the end of the talk. And thanks a lot for your attention.
Thank you very much, Professor Arbel. Do we have any questions?
So I'm interested in these BO functions because you didn't show any. I don't know what they are. What is their characteristics?
So the question is about the so there is the FBO algorithm, right?
A BO, and what are they? And concretely.
Concretely. So are you talking about the algorithm? How do we choose these functions here?
No, the algorithm is, I know it's the optimization algorithm, but you separate now the adjoint from the optimization and so on, but you said it works with the BO functions.
BO?
It's BO means bilevel optimization.
Both or something like this.
Yeah, I guess BO, I meant bilevel optimization, but...
bilevel optimization. I see. And I think a special kind. Okay, this is an abbreviation for this. I understand.
Yes.
Mm-hmm. I think in the standard bilevel optimization, this adjoint problem is solved together with the optimization problem.
You can solve them jointly.
You separate it because for a long time, so it maybe more than 10 years, and some people worked here. And then Oliver Stein from Karlsruhe, he worked on bilevel optimization. From there, I know. And that was here problems that were now really difficult problems here now to solve it is, and there's where the optimization was very important, and then they use for partial differential equations, etc. too. And I think then you separate now this here.
Yeah, I mean that would be interesting if you had the references for that.
Do you have concrete now here solutions for working with the kernel archives? Or the previous one you saw with working with the kernels?
So you mean concrete applications or?
Not concrete application. So the results which are now the kernels are better than, let me say, standard functions and so.
I mean, here the framework, you could pick any kernel. We only assume that it's bounded, so that would work for Gaussian kernel, Matern kernel. There are so many ones you could use. Yeah. And even you could relax this assumption and have something that is just integrable. Like you could replace this assumption by assumption on moments. Maybe like
Then also since this is a separable Hilbert space, so a kind of finite approximation would be fine, as you have shown, to represent theta parameter in a finite sum. So that would be some practical applications. But what I wonder is the following, actually. Why do we choose so sophisticated application area, apply everything in simply line search methods? So take an optimization problem and put a line search and use everything in terms of this.
Sure.
Why do we need a curve? Why do we need a neural network and hyperparameters?
Well, I mean, when you say line search, you mean like learning the.
No, we have two objectives. One is the objective, usual objective, and the inner problem is the line search.
Oh yeah, you could do that. Perhaps that would fit in the framework, maybe. Yeah.
Yeah. In that case, I will just check it. In that case, I don't need directly a line. When I put everything into a space of functions, then I will move something like dogleg in Levenberg-Marquardt methods. Most probably, I will find those curves that I should move in the search space in the usual optimization problems.
Okay, that's interesting. So are you talking about like using
just simple problem, just simple optimization problem?
Yes, simple optimization problem.
The line search will become search on a curve rather than a line.
Okay. So what we tried to explore a bit was to use this approach for optimizing functions using, Gauss-Newton, for instance. So when you apply Gauss-Newton, you need to solve
exactly.
Yeah. That's
that's
a very good...
that's the Gauss-Newton dogleg function that we want to find. Instead, they use thrust region methods to find the exact point that you should move. And if you use this method, you will find the same results, I guess.
Yeah, that's a very good point. And it's one thing that I found challenging was to get, I think in terms of algorithms, I think it would be a good idea. In terms of analysis for results, I thought a bit about it. It seemed to be hard, but if you have thoughts about it, I would be happy to discuss further.
Okay. Is there any other question, comments?
Here you have only now the regularization to parameter lambda, but I think when you saw the matrix and then you n times lambda.
Yes, that's.
But the n is gross, I think, with the data points or so, What is the n? N is the size of the samples data, or
yes, exactly.
but this affects now the regularizer, and this maybe becomes ill-conditioned and so, and then
it's you know, so the lambda, normally you would like it to adjust it in terms of the sample size. You want to decrease it as n increase, but here in this study we just fix it because normally people in statistics, they like to choose the optimal lambda in terms of n, and that would be actually the next one possible direction is to have even stronger generalization results where we allow lambda to go to 0. Here the n that appears in this expression is just an artifact. Like you can factorize
yes,
by and then you get it means just here the derivatives are kind of
you can put on the other side, etc.
Generally, you centralize the data and then you get rid of this n.
Yes, it depends. Sometimes numerically it can be worth having the n there, but I don't think it matters that much, but sure. Yeah. And of course, like as you increase n, indeed, you're right, you get this term here will be less and less well conditioned. However, the overall conditioning will always be of lambda. I mean,
you can choose lambda differently. I mean, so something like by Tikhonov regularization, then take from the L curves, etc. But it is now costly now, and to get each time the lambda choose now, then you can try and so something like this. I think a lot of problems here now. This is now.
Yeah, what's written here is the Levenberg-Marquardt method.
Yes, I think that would be that's a very relevant and good way to use this study, which is to solve the Levenberg method in a more efficient way, maybe.
Yeah, in the functional spaces.
Yeah, I mean, I didn't mention it, but we have a paper a few years ago where we studied the Levenberg-Marquardt method in functional space for some I mean for neural networks that have two layers and I can send you the reference for that, but I'm sure there is a lot of things you can do in that direction.
And all these are now the vector valued kernels, I think.
Vector
it should be now.
That could be a good extension, because here what we restricted to the case
that will be a good extension, I think. When you now go to partial differential equations, etc., you want to learn Hamiltonians, etc., you need then the size of this now will be that, and then you need now then some vector valued functions that will be now kernels can be easily extended to vector valued kernels then. That will be here in an extension, good, and that can be, I think, straightforwardly in this way.
Yeah, it's a very good point. Here, h is just a scalar, real valued function, but you can imagine, even for regression, you want to regress a vector, then it makes sense to have a vector valued function. And yeah, very good.
Okay.
So thank you very much for this nice talk and introducing us the kernel bilevel optimization.
Thank you very much. I hope you enjoy it. I hope it can be useful somehow.
Most probably, I will try to implement those algorithms that you have mentioned in some small, let's say, problems, which will be nice for me to learn better. I really thank you.
Are there other people or research groups working in the same direction with machine learning and then bilevel optimization?
So I mean, I have my students who are working on this problem. There are two. So the ones that showed. And then Julien, I think he's pretty much interested in bilevel optimization, so we work together on that. He has 2 postdocs, one that are kind of also looking at that. Yes, so other people are looking. I've seen that there's been some other people in the group I didn't know, but in fact they're working in computer vision, and they are in the end they are using that, but without knowing. So
I think it's nice because this area is now here is not very active bilevel optimization. It's revived, and it's interesting now because for a long time many problems have been solved or part, and the people left the area, and it's very nice to see now when it comes now in contact with machine learning now, and then. And there are here some, maybe if you are interested, some people worked on with the solution of partial differential equations in bilevel optimization. I can try to send now some papers, and that will be in a direction to see now here. Maybe you can try go now from perspective to this. So because this is the optimization of partial differential case was very here now active. Until 2020s and then 2015, then that stopped because many problems have been solved or new problems cannot be solved. But that will be now interesting to some people now. Tried it. Okay.
yes, definitely. That would be very nice.
Okay.
Thank you.
So before I stop recording, I thank you very much, Michael Arbel,
Thank you.
for your nice talk, and all the participants. I thank everybody. So I stopped recording.
Thank you.